In this video, we're going to be talking about how to find out local maximum and local minimum points. So, first of all, let's talk about what a local maximum point is and what a local minimum point is. So this is actually pretty straightforward. So a local maximum point is just a point that relative to the other points around it is greater. So basically, if we took a look at this function right over here, which is denoted as f of x, if we take a look at this point right over here, this point relative to the surrounding points, it's kind of like a maximum point, right? It's a relative maximum point or a local maximum point, right? And this point right over here is something known as a local minimum point, because relative to the surrounding points, the y value is less than, the surrounding other points. So if we take a look at kind of this crazy looking function right over here, right, the relative maximum point would be whatever this point is right over here, right? Because relative to all of the surrounding points, it's sort of like a maximum point. This right over here would be a local minimum point or a relative minimum point, because relative to the surrounding points, it's going to be, the y value is going to be less than, the surrounding points. Local maximum and minimum points, in this case, a local maximum point is just going to be higher than the surrounding values, but that doesn't mean that they're going to be higher than all the values, right? Obviously, I mean, if I pick this point right over here, this point is higher than, this point, obviously. But, relative to the surrounding points, this would be considered local maximum point. Now, there's actually something called absolute minimum and maximum points. So an absolute maximum point it's kind of how it sounds. It's like an absolute maximum point, right? It's going to be absolutely 100% greater than any other point on the graph. So an example of an absolute maximum point would be the graph of y is equal to negative x squared. If we take a look at when x is equal to 0, this would be considered a maximum point. However, it's not a local maximum point. It's actually an absolute maximum point, because this point right over here is actually greater than any other value you pick on this graph, right? Any other value you pick on this graph, it's going to have a y value that's less than if x is equal to 0. And an example of an absolute minimum graph would be y is equal to x squared, right? If we take a look at, and when x is equal to 0, notice how this point is always going to be less than, the y value is always going to be less than the other points. So absolute maximum and minimum points are sort of the highest and lowest out of all of the points, while local maximum and minimum points are just maximum out of kind of a certain interval of a graph. So maybe out of this interval right over here, this would be considered, this local maximum point, but it's not the maximum point for this entire graph. All right, now here's the important thing. So if I wanted to find out possible locations of a local maximum point or a local minimum point, so let's say if I'm given a problem where I have to find out at which x value is my local maximum point and my local minimum points located, well, let me just show you what to do. So let's say if I have a function f of x, and this is equal to x to the third power plus 2x squared plus 5. And let's say if I'm asked to find out at which x values do I have either a local maximum point or a local minimum point. So in order to do this problem, well, what you have to realize is that at a local maximum point or a local minimum point, the slope of the tangent line at that point is equal to 0. Right? When we're on a local maximum point, so let's say if we're on this point right over here, the slope of our line at that point is equal to 0, right? Or our slope at that point is equal to 0. And you can see the same thing for the local minimum point, right? At our local minimum point, the slope of the tangent line at that point is equal to 0. So slope is also equal to 0 at this point. Now remember that the slope of our tangent line, is also known as the derivative of our function. All right, so the slope of the tangent line is equal to the derivative of our function. So if I just take a random point on a function, just one single point, the slope of the tangent line, or the line that only touches this one point on the graph, the slope of this line is called the derivative. Okay, now what we're going to do is we're going to take the derivative of this function. So the derivative of f of x, also known as f prime of x, in this case, you'll just use the power rule. So you get 3x squared plus 4x, and then the derivative of a constant is equal to 0. Now, we know that at a local maximum point and at a local minimum point, our derivative of or our tangent line slope is equal to 0. So what I can do is I can actually set this equation right over here equal to 0. So what we've done here is we set our derivative equal to 0, because at the local maximum point and at our local minimum points, that is when our slope is equal to 0, right? So now we just have to solve this equation. So we can factor out an x. So we're going to have x times 3x plus 4 is equal to 0. X is equal to 0. And we have x is equal to negative 4 over 3. So from these values, we can conclude that at x is equal to 0, we either have a maximum point or a minimum point. And at x is equal to negative 4 over 3, once again, this right over here is either a maximum point or a minimum point. And, let's just confirm this. So our original function was f of x, I don't know why it's capital. This is equal to x to the third power plus 2x to the second power plus 5. Notice how there's a relative maximum point at x is equal to negative 4 over 3, and there's a relative minimum point at x is equal to 0. So this matches up with what we had. Now, if we wanted to know, so right over here, this x is equal to 0 and this x is equal to negative 4 over 3, this only gives us information on whether it's a maximum point or a minimum point in this case. And to find out specifically if it's a maximum or a minimum point, you'll have to do these steps. So first of all, you're going to draw a number line, and you're going to label the 2 points. So here is 0, and here is negative 4 over 3, okay? So notice how this number line is split into 3 parts. This part of the number line is from 0 to infinity. This part of our number line is from negative 4 over 3 to 0. And this part of our number line is from negative infinity to negative 4 over 3, right? All right. Now what we're going to do is we're just going to take random values. We're going to take one value from each of these 3 sections and plug it into our derivative, which gives us our slope of the function. And using that information, we can actually tell if it's a maximum or a minimum point. Check this out. This is actually pretty cool. So let's pick one point that's in this region right over here. So one point I can pick is x is equal to, x is equal to negative 2, right? Because negative 2 is in between negative 4 over 3 and negative infinity, right? So it's going to be somewhere here on the number line, let's just say. Okay. Now what I'm going to do is I'm going to plug negative 2 into my derivative. So I'm going to get 3 times negative 2 squared, which is 4, plus 4 times negative 2. And this is going to evaluate out to be equal to. So this is 12. This is negative 8. 12 minus 8 is equal to 4. So we get 4 right over here. Now, because our derivative at x is equal to negative 2 is positive, that means that our function is increasing at this region of the graph. Okay, so if you plug in a random point from one section of your kind of number line that you've drawn, plug into the derivative, and you get out a positive value, what this indicates is that, well, because the derivative represents the slope of your tangent line, right? I said how the derivative represents the slope of the tangent line. So if the slope of the tangent line is positive, that means your slope is increasing, right? So that means that from negative infinity to negative 4 over 3, well, obviously not including this value, but that means that your function is actually increasing from that point. All right, so from negative infinity to negative 4 over 3, not including negative 4 over 3, your function is going to be increasing. And you can actually see it in this graph, right? From negative infinity to negative 4 over 3, not including this point, obviously, because this point right over here has a slope of 0, we said, right? So it's not going to be increasing, nor is it going to be decreasing. So that's why we use open parentheses. But from negative infinity to that point, notice how our graph is just constantly increasing, right? It always has this positive slope. All right. So kind of just the key idea to know. I know I've been yapping a lot, but if the slope thingy works for one value, so if you plug in one value and you get out this positive slope, well, it's going to work for all the values that are in between here, right? If I plug in x is equal to -3 into my derivative, I'm going to get 3 times -3 squared, which is 9, plus 4 times -3, and this evaluates out to be 15. So notice how you can actually try out as many values as you want, but your slope is always going to be increasing from this. Now, from the interval from -4/3 to 0, well, what's a number in between these two values? And let me just keep it simple. Let me just pick -1, right? -1 is in between these two values. So what I do, once again, I plug -1 into my derivative. So I get 3 times -1 squared plus 4 times -1, which is -4. This is just 1. 3 times 1 is 1, and then this is going to be -4. So this is going to be equal to -1. Now, because our derivative is a negative value, this means that the slope of our tangent line at that point is going to be negative, right? And if we have a negative slope, our function is going to be decreasing from, in this case, -4/3 to 0, right? Now, imagine this. Imagine if we have something that's increasing, and then after that, we have something that's decreasing. Well, at this point right over here, at this point, which in this case is -4/3, this is actually going to be a local maximum, right? Kind of just from the arrows, you can kind of see how, right, you have something that's increasing, you have something that's decreasing. So at this exact point right over here where kind of these two arrows kind of intersect, I guess, well, you're going to have this local maximum point, right? All right. Now let's pick a number from 0 to infinity. Let's just pick the number 1. All right. Always try to pick the simplest values to plug into your derivative. So if I plug in 1 into my derivative, I get equal to 7. Now, because our derivative is positive, well, that means that our function is going to be increasing from 0 to infinity, right? And notice here, from -4/3 to 0, our function is decreasing, right? From 0, not including 0, but from 0 to infinity, our function, we said, is increasing. So that means that at exactly x is equal to 0, we're going to have a minimum point, right? Because we've decreased and then we've increased. So this point right over here has to be a relative minimum point. And you can see this on the graph, right? This has to be, if our function is decreasing and then after 0 it's increasing, well, that means that 0 at x is equal to 0, it has to be a relative minimum point. So kind of the key summary for this is, if our function is increasing and then decreasing, it's going to be a relative maximum point. If our function is decreasing and increasing, it's going to be a relative minimum point. And all you have to do is just pick one value from your number line, plug it into your derivative. If it's positive, then it's increasing. If it's negative, then it's decreasing. I want to find out my local maximum point, and I want to find out my local minimum point. Let's just say. So how would we do this? We take the derivative of this function. So it's going to be 4x to the third. 4x to the third plus 9x squared. All right, now what we're going to do is we're going to set our derivative equal to 0. All right, so that's the second step. We set our derivative equal to 0 because, once again, remember that at local maximum and at local minimum points, the slope at that point is equal to 0. Right? So that's why we set it equal to 0, because this gives us the coordinates of the x coordinates of our point. So to do this, you can just factor out an x squared for x plus 9 is equal to 0. So either x is equal to 0 is a potential minimum or maximum point, or at x is equal to -9/4 is a potential minimum or maximum point. Okay? Now, once again, we're going to do the same trick we did before. We're going to draw a number line, and it's going to divide our number line into 3 sections. This section right over here is from -infinity into -9/4. This right over here is from -9/4 to 0, and this is from 0 to infinity. We're going to pick one number from each of these sections, plug it into our derivative, see what it spits out, and then determine whether if it's increasing or decreasing. So let's pick a number from this section. Let's just pick, I don't know, try to make it easy. Let me just pick -3, okay? So if I plug in -3 into my derivative, I get 4 times -3 to the third power plus 9 times -3 to the second power. negative 3 to the third power is all going to be equal to negative 27. So we get a negative slope. So from this region right over here, we get a negative slope. So that means that our function has to be decreasing, right? Because if our slope is negative at x is equal to negative 3, then that means that from this interval right over here, from this region of our number line, well, that means that our function is going to be constantly decreasing from this interval, okay? If it works for one value, it'll work for the rest of the values. You can pick negative 4, you can pick negative 5, plug those numbers into the derivative, and you'll notice that you'll always end up with the negative answer, meaning that you'll always have a negative slope, which means that your function is always going to be decreasing because you got a negative slope. All right, from negative 9 over 4 to 0, let's just plug in negative 1. So if I plug in negative 1 into my derivative, I get 4 times negative 1 to the third power, which is negative 4, plus 9 times negative 1 to the second power, which is just 9. Negative 4 plus 9 is 5. Now 5 is a positive slope, right? If we have a slope of 5, this is going to be a positive slope, meaning from negative 9 over 4 to 0, our function is going to be increasing. And finally, we have from 0 to infinity. So let's just pick out a random number. Let's just pick the number 1. Let's plug in 1 into our function, and into our derivative for the function, and then we get 4 times 1 to the third power, which is just 4. 9 times 1 to the second power is 9. Once again, we get a positive derivative, meaning that our function from 0 to infinity is going to be increasing once more. So, to answer the question we've been looking for, let's try to find out where our local maximum point is. Is there even a local maximum point in the first place? Oh, take a look. So from negative infinity to negative 9 over 4, our function is decreasing. All right. And then from negative 9 over 4 to 0, our function is increasing. And then from 0 to infinity, our function is still increasing. So it's going to be increasing on forever, right? We see how from 0 to infinity, our function is just going to keep increasing, meaning that there's actually no maximum point. The function is just going to keep increasing on forever. So there's actually no, local maximum point, or there's not even an absolute maximum point because, it goes on to infinity. Now, is there a local minimum point? Negative infinity to negative 9 over 4, our function is decreasing. From negative 9 over 4 to 0, our function is increasing, meaning that at this specific point, in this case, at this specific point, x is equal to negative 9 over 4, well, our function is a local minimum point. And actually, this isn't a local minimum point. This is actually an absolute. This is actually an absolute minimum point. This is actually an absolute minimum point because is there any other minimum points in this graph? No, this is the only minimum point we see in the graph, meaning this has to be the lowest minimum point in the graph, right? It has to be the lowest of the low. Because there's no other low points. If I wanted to find out the coordinates for the absolute minimum point, what I would do is I would take my x value of negative 9 over 4 and I would plug it into my original function. The original function gives out the actual coordinates of the points. The derivative only gives the slope. So in this case, if I actually wanted to find out the actual coordinates of our absolute minimum point, I would actually have to plug it into our original equation, not the derivative. So don't get that confused. So if I plug in negative 9 over 4 here into my x value, I get negative 9 over 4 squared plus 3 times negative 9 over 4 to the third plus 2. All right, now I'm just going to use my calculator. Okay, this is to the fourth power, and then this is plus 3 times negative 9 over 4 to the third, and then plus 2. So our absolute minimum point is at the coordinates. So we know the x coordinate for our point is negative 9 over 4. And then if you plug all of this into your calculator, the y coordinate of your point will be approximately negative 6.54. And let's see if I'm correct. I actually don't know if I just made this problem up on the spot. So hopefully, fingers crossed, this would be the correct answer. All right, so there's 3x to the third power plus 2. our absolute minimum point is at, okay, x is equal to negative 9 over 4, which is the same thing as negative 2.25. And you see, as the y-coordinate of this, and notice how from there, the function just keeps on increasing and increasing, okay? So actually, there's actually not really a relative maximum point because, first of all, the function goes on forever, but this wouldn't be considered a relative maximum point because, these points around it are greater than it, so there's actually no relative maximum point, just one absolute minimum point. Now, you can also have weird scenarios like this. So let's say if you have f of x is equal to x to the 2/3 power, and you want to find out where does it have either a maximum point or a minimum point, whatever. Where is that located? So we're going to do the same steps we did before. We're going to take the derivative of it, and using the power rule, we get 2/3 times, this is going to be x to the 1/3 power. So this is just the derivative of x to the 2/3 power. All I did was I just dropped the power, and then after that I subtracted 1 from it, so 2/3 minus 1 is x to the negative 1/3 power, and because it's a negative exponent, I just brought it down to the denominator. In the problems before, right, remember how we saw that the points where the x values where our function had a derivative of 0, these right over here are something known as critical points, okay? So these values right over here that we've seen before are something known as critical points. We have our equation, right? And what we do is we actually set our denominator equal to 0. So the critical points of a function are located by setting either the derivative equal to 0 in this case, or it can be when our denominator is equal to 0, okay? So in this case, in the first two examples, you saw that you found out the critical points of our function by setting the derivative equal to 0. However, if you see any x's in the denominator, well, what you do is you set that denominator equal to 0. At x is equal to 0, our denominator is equal to 0, right? And our derivative is undefined. So x is equal to 0 is actually a potential critical point. So believe it or not, setting the denominator equal to 0 will actually give you other potential critical points. And you might be asking, and this is actually the graph of it, right? And you can see this is, there is actually a absolute minimum point at x is equal to 0, right? And you might be asking, why do you set your denominator equal to 0? Why does this strategy work? This strategy works is because, well, if you have a function where you have a really sharp turn, so I'm just going to use, to the absolute value of x, okay? Now at x is equal to 0, this function isn't differentiable. You cannot take the derivative of the absolute value function at x is equal to 0. The reason why is, as you approach 0 from the left-hand side, so as you approach 0 from the left-hand side, the slope of your tangent line is equal to -1. However, as you approach 0 from the positive side, so as you approach 0 from the right-hand side, slope is +1. So at x is equal to 0, there's not really going to be a derivative. Don't get this confused with when you have a parabola. Absolute minimum point, what you notice is that our function, the slope of our function, is becoming less and less and less steep, right? So at this point right over here, our slope is going to be equal to 0, right? But for our absolute value function, our slope does not get less and less steep. Our slope just stays the same, and there's this sharp turn. So in this case, at x is equal to 0 for the absolute value function, this function isn't differentiable because, this side, our slope is -1, right? When we approach this point from this side, our slope is -1. When we approach 0, x is equal to 0 from the positive side, our slope is +1. So, obviously you can't be two slopes at once. So it's not going to be differentiable. And in this case, this is kind of the same thing, right? At x is equal to 0, when we plug in x is equal to 0, our function is not differentiable at that point, meaning that in this function, there might be a potential sort of sharp turn in that function. Okay, so just to recap everything, the definition of a critical point is a critical point of f of x occurs at x is equal to c. So x is equal to, some x value if f prime of c, so if the derivative at that point is equal to 0, right? The derivative of, in this case, it can be a maximum point, it can be a minimum point, but, the critical points, they can give possible maximum or minimum points, okay? Or this is what we talked about before. F prime of c is undefined, but f of c is defined at x is equal to c. So what this basically means is, our derivative is undefined, right? Remember, if we have f prime of c and it's equal to 1 over 0, let's just say, and it's undefined, then this also gives you a potential critical or, absolute maximum or minimum, right? So if our derivative is undefined at some x value, like, kind of what we saw with the absolute value function, right? At x is equal to 0, the absolute value function has no derivative, it's undefined, right? This can also give you a critical point. But the thing is that the function itself has to be defined at that point. So the actual graph of the function itself has to be defined at that point. So if I have the absolute value of x, if let's say at x is equal to 0, so let me just draw this again. So if I have an absolute value of x and at x is equal to 0, our function wasn't defined, so I had an open circle here, then this would not be considered a critical point. Actually, in this case, this is actually really interesting. There would actually be no minimum point in this graph. Think about it, right? If you start from, let's say, x is equal to -9, and you get closer and closer to x is equal to 0, you can get infinitely closer to x is equal to 0, right? And yet, you can still get infinitely closer, and it would still not reach the y value of 0, right? Because a minimum point, right, you're trying to look for the lowest y value. However, you can keep on going lower and lower and lower if, x was not equal to 0, right? You can get infinitely closer to x is equal to 0, but, you'll never get to the actual y is equal to 0 line. I know this concept might be a little bit confusing, so if I, maybe show you on Desmos, so if I have the absolute value of x, right, I can get, imagine if this point was undefined, well, then I can get infinitely closer to x is equal to 0. I can get infinitely closer, right? I can get infinitely closer, but you notice how I can always go lower, right? I can always go lower. I can always zoom in and I can always go to a lower y value, right? So there would actually be no minimum point at y is equal to the absolute value of x if x was not able to be 0. All right. So in this case, types of critical points. So we talked about how critical points can be local maximum or minimum points. And we saw how we can actually take the derivative of our function to actually get the critical point. And in later videos, I'll actually teach you what the second derivative actually tells us. So you actually take the derivative of our function twice and actually gives you more information about the function. So that's pretty cool. Critical points can also give you information on sharp corners. We already talked about that, right? Y is equal to absolute value of x. And critical points, I didn't talk about this, but critical points can also give you locations of vertical asymptotes to 1 over x squared. Well, if you actually take the derivative of this, you get y is equal to, let me see. So this is actually x to the -2 power, so you can actually do the power rule. So you get -2 x to the -3 power, so you get -2 divided by x to the 3rd power as our derivative. And notice when x is equal to 0, our derivative is undefined, right? So we said how a critical point occurs when either our derivative is equal to 0 or when our derivative is undefined. And at x is equal to 0, our derivative is undefined, meaning x is equal to 0 is a critical point and a potential minimum or maximum. However, if you graph this out, let me just zoom back out, what you'll notice is that this is a vertical asymptote, right? There's actually no maximum point because it just keeps going on forever. So, yeah, the thing about critical points is they can give you local minimum or maximum points, but at the end of the day, you still have to check, either using a graphing calculator or, the number line method we used, right? So, yeah, critical points don't guarantee you to get your local minimum or maximum. All right, so that's also something to know.